So we're going to continue with gas laws today. We already in the Do Now reviewed Boyle's law, which shows the inverse relationship between volume and pressure at constant temperature. And this all fits in with a better understanding of gases, the properties of gases, the kinetic molecular theory. And now we're starting to go through many of the gas laws, looking at the relationship among variables we've talked about. So with Boyle's law, we know that we have the inverse relationship between pressure and volume. Again, when you multiply variables on the same side of the equation, they have an inverse relationship. As the pressure goes up, the volume goes down. What we're going to look at today are some additional gas laws, and we're going to introduce the temperature concept here. We're first going to look at Charles' law, which shows the direct relationship between volume and Kelvin temperature. Hence, in the Do Now, we looked at Kelvin. And we're also going to look at the direct relationship between pressure and temperature, and again, capital K for Kelvin. We've got some additional gases we're going to gas laws we're going to explore as well, and we'll take them as they come. First up is Charles' law. We're going to look at the direct relationship between volume and Kelvin temperature. And I'll set up a whole bunch of videos in your Google Classroom in case you want to take a second look-see at anything. Okay, so with Charles' law, there's a direct relationship between volume and Kelvin temperature, and we're going to explore this relationship in the lab either on Friday or next week. Jacques Charles showed this relationship, and he showed that when you heat a gas, it expands. Its volume increases. When you cool a gas, it contracts, and you'll see that the volume decreases, provided that the pressure is held constant. Again, you must do these problems with Kelvin temperature. If you do it in degrees Celsius, you'll crash and burn. The game's over. Be very careful here. Kelvin temperature. So again, as we talked about initially, you just add 273.15 to the temperature in degrees Celsius to get Kelvin temperature. This shows the direct relationship between volume and Kelvin temperature, and the same way we expanded upon this with two different sets of conditions, we can then derive V1 over T1, that is the volume and temperature under the first set of conditions, is equal to V2 over T2, the volume and temperature under the second set of conditions. You can see it graphically as well as pictorially here. The direct relationship between volume and temperature. As you increase the temperature, you see the volume increases as well. You have a linear plot, and you will be generating such a plot in the laboratory. We'll heat up a gas, and then we'll cool it, and we'll look at the change in volume for the gas. You actually have two labs in this chapter. They're both very fun, and I think you'll enjoy both of them. Pictorially, what's shown here is if you have a balloon and it's filled with air and you put it into liquid nitrogen, which is very cold, you will see contraction. The volume decreases significantly. So temperature greatly affects the volume of a gas. You don't find that with solids or liquids. So when you decrease temperature, you decrease the volume. Atmospheric pressure decreases with increasing altitude, so when you look at the relationship between volume and temperature, it can be slightly different. For example, in Denver, it's always an issue with cooking. Chefs that usually cook in Denver, if they come to a competition in New York, they usually find that they really have to alter their recipes because the way things cook up there is not the way things cook in other parts of the country. We're not really going to get into it all that much. What we are going to focus on is being able to understand the relationship between volume and temperature, and then being able to do the calculations, which are very, very simple if you're comfortable manipulating variables, and you'll implement a few tricks as we work through. The first one says that krypton occupies 4 moles of space at 10 degrees Celsius. Highlighted in green is your first set of conditions. Volume and temperature specified. We'll write those down in a minute. If the temperature is increased to 50 degrees Celsius, we want to know the volume that krypton occupies at that temperature when pressure remains constant. So I like to get the information down. I like to manipulate the formula, and then I will solve. And make yourself a note in the margin that you must do this in Kelvin, or you're going to create a complete and absolute mess. Sort of like my daughter's room. Can't get her to clean it up. Alrighty. Here we go. So, it says krypton occupies a volume of 4 mils. Now, in Charles' law or Boyle's law, it doesn't matter if the volume is in mils or liters as long as you're consistent with it. And the temperature is 10 degrees Celsius. I like to immediately change that to Kelvin because I'm less likely to make a mistake. I'm going to add 273.15 to that as we discussed in the do now, and we're going to get 283.15 Kelvin. No degree Kelvin, just Kelvin. We're looking for the volume under the new set of conditions where T2 is 50 degrees Celsius, and again, as soon as I write degrees Celsius, I'll put a line through it and I'll convert to Kelvin. You are so much more likely to have success if you do that right away. Charles' law says that V1 over T1 is equal to V2 over T2. And I want to solve for V2. Something is divided, so the way to undo the division is a multiplication. And now I have V2 is equal to T2, 323.15 Kelvin. Is that big enough in the back? You want bigger? Are you good? Thank you. V1 is 4 mils. T1 is 283.15 Kelvin. That's what I got. So you have 4.57, maintain the unit, mils. I always check to make sure that my answer makes sense based on the relationship between the variables. I can see that temperature increased, so the volume had to increase as well, because volume and temperature are directly related. When you divide variables on the same side of the equation, they're directly related. They behave in the same manner. I like to move variables. I put the quantities in at the end. If you also follow your units, you'll be more apt to have the correct units at the end. Pretty easy. Yes, yes? The second one's a smidge harder, but I'm going to show you a trick that'll make it easier. In the second problem, it says chlorine gas occupies 5 liters of space at a temperature of 200 degrees Celsius, which I'll immediately get to Kelvin so I don't do anything silly. Now the volume's going to decrease. If the volume's going to decrease, what would you predict the temperature's going to do? Decrease as well. They are asking for the temperature in degrees Celsius. You still must do the problem in Kelvin, and then you'll subtract 273.15 at the end. I have V1 over T1 is equal to V2 over T2. And now I want to solve for a variable that's in the denominator. You can. What I do want to point out is a cute little trick that you may never have seen before.
Wait, Dr. Kim,
what?
Wouldn't you just divide by V2?
No, because that's going to give you 1 over T2, and that's the point I want to make. I was just letting you catch up. I just want to show you a cute little trick. Sit tight. It's all good. What I like to do when I'm solving for something in the denominator is I like to do a double reciprocal. I'm going to flip both fractions over. Now that at first may bother you, but look, it's perfectly legitimate. 3 over 1 is equal to 3 over 1, right? If I flip them both over, is 1/3 equal to 1/3? Sure it is. I'm not saying 3 is equal to 1/3. That's why you have to flip them both. When you flip them both over, now what you're solving for is in the numerator, which you always want. Now if you multiply both sides by V2, that will cancel. That goes there, and now you have T2 is equal to V2 times T1 over V1. So your T2 in Kelvin is 142, and you'll subtract, just subtract 273, make it easy. It's all going to come out the same anyway. I'd actually like to get rid of the 0.15, it's annoying. Negative 131 degrees Celsius. So when you're solving for temperature, make sure you get it up in the numerator. If you don't like the double reciprocal, then cross multiply first and solve whatever's easier for you. But this is a great little trick. If you'll adapt to it, you'll like it, and you'll find solving for denominator variables much, much easier. Questions here? Make sure your answer makes sense. The volume decreased, the temperature decreased as well. It really doesn't matter. Whatever's easier for you. You know, in honors they say 273.15, but honestly when you go to college chem and AP chem, we just do 273 to make life easier. So whatever's easier for you is fine. If I get negative 131 and you get negative 130, as long as you maintain sig figs, I'm good with it. All right? Okay. So Charles' law shows the direct relationship between volume and temperature. Another gas law shows a direct relationship also with temperature, but the variable we're going to be looking at here is pressure. The direct relationship between pressure and temperature. And this you could see, for example, why you don't put aerosol cans in very, very high temperatures. The pressure gets so great that it just goes boom. The college textbooks show this as Amontons' law. Some other textbooks say it's Gay-Lussac's law. I'll take it either way, but I listed it as Amonton. It shows the direct relationship between pressure and Kelvin temperature. You're going to hold volume constant. When temperature increases, gas pressure increases. So you can see the direct relationship between the divided variables, pressure and temperature. You can expand upon that, two sets of conditions. Graphically, it looks grossly the same. You have pressure on the y, temperature on the x, the direct relationship. If you have a can and you heat it, you will see pressure is exerted. As you increase temperature, you increase pressure. If you turn the flame off, so you're decreasing temperature now, you're removing the heat, the can implodes because the pressure has decreased markedly with the decrease in temperature. Direct relationship between pressure and temperature. We'll walk through the first example together. I'll let you try the second example. It says a gas exerts 105 kPa of pressure on the walls of a 5-liter container. The volume is specified. The temperature is 30 degrees Celsius. That's the first set of conditions. Highlighted it in one color. Now you're going to increase temperature to 50, and you want to know the pressure. It didn't say anything else about the volume. So they gave you the volume, but it doesn't change. That means the volume's constant. Doesn't factor into this particular type of problem. If the volume changed as well, then you would factor it in, and you'll see that in a subsequent gas law. So in this first example, what we've got is you've got P1 at 105 kPa. Again, get familiar with units of pressure. We don't need the volume. T1 is 30 degrees Celsius or 303.15 Kelvin. We're looking for P2. T2 is 50 degrees Celsius, and we know right away we need to get to Kelvin or the game is over. This is going to look very, very much like Charles' law, but we have pressure instead of volume, so this is Amontons' law. We've got P1 over T1 is equal to P2 over T2. We're solving for this. We'll move that over. Most of you are very strong with variable manipulation, which will help you greatly in this chapter. So we've got P2 is equal to T2 times P1 over T1 and this is 112 kPa. And make sure your answer makes sense. The temperature increased, you would have predicted the pressure would do the same, and it does. Questions here? You're comfortable moving variables? It's much easier to move variables than it is to move quantities. Also keep track of your units to make sure you've got the correct unit at the end. I'll take 1 point off if you don't have a unit or you have the wrong unit. I would like for you to try number 2. It's a little harder, but it's really similar to a previous problem. So 2 is at the top of the screen.
In that kind of case where you are finding for Celsius, then you just leave it and stuff.
No, because the direct relationship is with Kelvin temperature, so don't do that. That makes a big mess.
And Kelvin's 273.
273.15. You can just add 273. I think it's just easier. It's really not going to change the value in any regard. But it's not only important to be able to plug and chug, you also have to understand the relationships. How'd we do? Don't look if you didn't finish yet. Yes, yes? No, 5.00 would be 366, honey. Oh, oh, he said 2. He said 2, didn't he? What'd he say? I did too, but it's okay. Actually, it doesn't, because when you go to subtract, you're just maintaining decimal places, so this is one where you'd get away with it. Yeah, but what you were at 3 sig figs here, and then you subtracted, so that's one you'd get away with, because when you subtract, you just go to the least number of decimal places, and you're still maintaining no decimal places. You can. Whatever's easier for you is what you should do. Mrs. Guzzetti and I had an argument about this one day. I said, how would you do this? She goes, well, okay, let me rephrase. I presented it as I always flip things over and then solved, and she goes, well, I probably would have cross-multiplied and solved. And I said, well, which way do you teach the kids? She said, oh, I teach them to cross-multiply and solve. I said, oh, okay, well, I'm going to teach them this way. So you can do whatever you want as long as it's right.
You know Miss Gazzetti's coming back.
I
No, she's
do.
not.
Hang on, guys, we're on videotape. So, yes, I saw her the other night, and I look forward to seeing her. In any event, in any event, in any event, in regard to your quiz, we have a whole lot more to cover today. You guys are like a class behind, so I've got to start to bridge the gap. But in regard to your quiz, and I will give you practice time in a little while, this is what I'll be assessing. In regard to gases, we'll be looking at Boyle's law, similar to the do now, actually just like a plug and chug type thing. Charles and Amontons law, which we just hit, and I think you found relatively straightforward, but I think you have sugar coma from yesterday. In regard to nuclear, also exactly what I told you. All the nuclear lessons were recorded in the event that you missed anything. Balancing nuclear equations, neutron to proton ratio, radioactive decay series, where you start with 10 milligrams of something and it's gone through X number of half-lives, what remains. So that is your quiz. It is a very, very, very simple quiz, like super, super easy. In regard to classwork problems that are similar, you know, I wrote 3.3, but that's not right. It's 3.2a. Your quizzes are ahead, but your classwork is 3.2a. It'll be 1 through 11. And off the nuclear, it's going to be classwork 3.x. I'd like to say all, but it's really more the backside than anything. You answered? I answered it? Okay. So I'm sort of in the way here. Let me slide this over. Yes.
Will we have to be able to identify, like, Boyle's law?
I didn't ask you to identify the laws for this. Like, when the test rolls around in terms of multiple choice, I probably asked for one of them. It's kind of funny because Boyle's is the one at constant temperature. So if you think about it, like boiling water is 100 degrees Celsius, temperature's then constant. That may help you, but it's pretty straightforward. Questions here? So that is as far as your quiz goes.